Okay, good crowd we have here. Hi, everybody. I am looking at the attendee list, and what an illustrious attendee list we have. So I'm honored to be kicking this off, and I've got a little story to tell about doing some investigations following the 2010 Maule Chile earthquake. I am going to share. Okay, and Kristen, everything looks good on your end?
Yep, looks good.
Yeah. Okay. So, yeah, you guys know I'm a professor at Cal Poly. I also have a CPT company in Chile, which I am a founding member of. And that came about because after the 2010 investigations, we were trying to do CPT work down there, and it was either infeasible or cost prohibitive. And so we saw an opportunity and started getting equipment down there and continue to do CPT work as a subsurface contractor. The inset map on the left shows the location where this tailings dam failure was. So Santiago's up on the upper right, and our location is about 2.5 hours south of Santiago along Route 5 near the town of Talca. And this tailings dam, this was a defunct gold mine. It had stopped operations, I believe, in '83, and what we could piece together was this was the construction of the tailings dam in 4 phases. So there was an initial phase of ponding with coarse material for the dam, and then there was a downstream dam that was placed and then expanded, and then this was the state that it was left when the gold mine closed down. And you can see that there might be some issues because this tailings dam is floating on some of the ponded material, and upstream this one's also on the ponded material. And as we know, that's a no-no when you're constructing tailings dams. So along comes the magnitude 8.8 earthquake. And, right, I mean, this was, I believe this was the 5th largest earthquake in recorded history until the Tohoku event happened. And then it got bumped down to the 6th. But this was a major event, and the ground shaking was distributed over a vast area. And here the rectangle shows roughly the rupture plane, and the red circle is showing the relative location of where this tailings dam is. And from the instrumentation that was close to the site, we estimate around half a G of strong ground shaking at this particular location. So once the Santiago airport was opened, I was part of the first team that was in there. I was on team, I think I was actually before Team A. I was there with Christian Ledesma and Montalva also was there. And we started to get the investigations going. And here was the initial pictures of the tailings dam failure. So this is standing at the mid-dam, looking kind of obliquely downstream. And you can see that there was a massive slope stability failure. And this is from the other angle. So to the left was upstream, to the right is downstream. And you can see that there was a massive failure. And all these little white spots here ended up being sand boils. Here's an aerial view. Sorry, it's a little bit fuzzy. So this was the mid dam here. Here's the upper dam, and the lower dam would have been right in this location. Kristen, can you guys see my cursor?
I can see your cursor. Mm-hmm.
Okay, good, thank you. So you can see that it was a massive failure. You can see flow characteristics here, centerline cracking along the ponded material, all the white areas are liquefaction. So there was A little bit of liquefaction on the uphill dams, a little bit came out here, but then tons of liquefaction on the lower portion. Here's a before and after. So before, this is the lower dam, this is the mid dam, this is the upper dam. After, and the reason that it's all black and shiny is because there was, following the failure, there was at least 2 lawsuits. One was about the deaths of the people. There was a caretaker that lived down here with a family, and they died in the debris flow. The other lawsuit had to do with the environmental impacts of this material. And one of the outcomes of the environmental lawsuit was that they had to put this geomembrane across the top of it to try to prevent any of the heavy metals and other things getting into the creek. So that was part of the settlement. So you're going to see this black geomembrane as we move forward. So again, before, after, quite a big run out on the order of, the furthest reach was about 350 meters. And here's some pictures from the reconnaissance effort. Sand boils. Here's lidar images that Rob King did during the investigations, during the gear investigations, but he was on a subsequent team. We sent a bunch of teams down, and he was on one of the latter teams. And so here I'm showing the images of the undisplaced and the displaced material. I've given this talk a couple times now, and you can imagine that the interested parties are mining parties. So I've given this talk in Santiago to a group of academics, but also mining engineers and mining company executives. And then the other place I've given this talk is in Butte, Montana, where the mining is essentially ceased, but there's massive tailings dams that are looming above the city. And so you can imagine when I give it to those audiences that I have their rapt attention. So I'm going to digress a little bit into the physics. And recently I've been looking at tying debris flows and flow failures together. Here I live in California and work on liquefaction, and I work on debris flows and flow failures. And so I was interested in the overlap of the physics. And there are some commonalities. We can have liquefaction or debris flows triggered by a number of different mechanisms. For our particular failure, we're looking at seismic soil liquefaction. But when we get to flow state, it's all steady state shearing. And we've got our excess pore pressures, and it doesn't behave like a Newtonian fluid. It behaves like a Bingham fluid. And then the runout mechanisms, it's dependent on the material type. It's highly dependent on the gradation and the material type. And when we look at debris flows, if you have a very broad gradation, you have this effect called, in the debris flow literature, it's called granular temperature. But it's more like transmission of kinetic energy throughout the material that can enhance the runout distance. And then is our material flowing in a laminar or turbulent manner? And then do we have any changing stress conditions? And with our tailings dam material, generally we're dealing with a contractive material that's going to be above the critical state line, where when it's triggered or we start stressing it, particularly in a seismic manner, we hit the instability line and then we start to get flow. And, 350 meters, that's a large strain. So we're definitely for a large portion in the steady state range, and where we've hit critical void ratio, and then we're just at our residual strength of that material. And here, just a schematic of what is a Bingham fluid. It's a rate dependent like a Newtonian fluid, but we have an initial yield stress that we have to exceed. And I'm going to towards the end of the talk, I'm going to get into some run-out discussions. But again, these categories of contributing factors to the run-out. How fast is the drainage? Are we maintaining those excess pore pressures, or are they dissipated quickly? Here with tailings material, we're often talking about, the ponded material, we're often talking about non-plastic silts, which have very slow drainage. So they're slow to generate the excess pore pressures, but once they generate them, they're very slow to dissipate as well. For our material here, I don't imagine that there would be any contribution from this granular temperature concept because it's fairly uniformly graded. Fine sands, coarse silts. I'm not even going to try to conjecture if we had any turbulence in it. I would guess it was, well, here I am conjecturing. I would guess it was mainly laminar flow that we're dealing with, but it's really hard to make any guess. And then the slope was fairly constant for our tailings dam, and there wasn't really a berm at the bottom. It just ran out till it had dissipated itself and thinned out and released those excess pore pressures. Okay, so back to our aerial view. What we wanted was to do a thorough investigation to try to characterize the subsurface conditions. And, you know, following the gear investigations, I had an interest in this, but trying to mobilize to do the subsurface investigation, as you guys know, it takes a certain amount of momentum to get those things going. Well, the lawsuit that was going on in Chile, the environmental lawsuit, had funded the SPT investigations, and Christian Ledesma at Católica University was running that, and I had been down there, and he said, you know what, we went back to Las Palmas, and I said, well, you did? He said, yeah, we got funding to do 5 SPT, and so that really got me going, and I said, okay, well, then we're going to mobilize and do some CPT and some shearwave velocity, and then we'll have a whole suite of subsurface investigations, and I thought, this is great, you know, because I've dealt with the flow failure case history database before, and it is meager. Sometimes you'll have, you know, a particular case history, and it'll just have, well, I mean, we have to extrapolate a lot in geotechnical engineering, but very minimal data. And so I thought, wow, this is a great situation where we could maximize the amount of subsurface data on this particular case history. And really turn it into, what I want to do is turn it into like the gold standard for doing flow failure investigations. We can't always get all the way there, but that was the goal for this. So here we are on site. This was, I want to say this was 2017. And we hit it right during a massive series of rainstorms. So you can see that it's kind of a mess. This is some of the old mining facility equipment. This was also where, let's see, the caretakers, they had lived over here. You can see the plastic sheeting that covered the whole place. I'm sure that cost a pretty penny to sheet the whole thing. And now I'm showing where the SPT investigations that were done by Católica University by Christian Ledesma. So he was able to fund 5 SPT, all in the intact material, trying to get an idea of what the intact ponded material looked like, and also poke through the dams themselves and see what they looked like. SPT. Okay, so then my role is to come and do CPT. Here's our company in Chile. This is our first truck. And I like to show this picture because this was a real picture. The lighting was awesome. So we use this for all of our advertising. Unfortunately, because of the messy conditions of the site, we couldn't get the truck up there. So we used portable CPT equipment. What you see here is this is a hydraulic ram, same hydraulic ram that you find in the truck. So we can have the same results. We just need to develop the reaction weight. So there's a platform that we bolted to, and then those white containers in the back, those are water containers, and we put those on the platform and we fill them up with water. and we can achieve enough reaction weight. I mean, plenty reaction weight for tailings material or for tailings dam material. And we carted everything up in this 4x truck that we have. So this is our portable CPT equipment. And then you see over here is our geophysical equipment. And there's Tristan Gebhardt, who's the grad student that was on this project that did a bang-up job. So here we are in business. Here's the hydraulic ram. Here's the pump. Over here underneath the plastic sheet near Dave Frost is our computer equipment and our data acquisition system. So it looks a little bit janky, but the results we get are just like the results that you would see in coming out of a CPT truck. So we had good results. The drawback of using portable equipment is the setup and the teardown. Whereas, you know, if we had the truck up there, we could have probably done at least 2 CPT a day, maybe more. With the portable equipment, we could only do 1 CPT a day because it would take us, you know, at least a couple hours to do the setup and then a couple hours to do the teardown. Pushing the cone, you know, only took a half an hour. And then with the inclement weather, it was on top of that. So very difficult field conditions, but we were able to achieve the minimum goal that we were after. And then here, I was doing shear wave velocity measurements with a passive SPAC array. Again, there's Dave Frost. He came down because he just wanted to hang out and do some field investigations with us, and he had a personal interest in seeing this this investigation go through. So with the passive SPAC analysis, we measure ambient waves, and then we invert a shear wave velocity profile from that. And we had pretty good control on the stratigraphy because we did them adjacent to the CPT. So here would be final shear wave velocity profiles that we inverted. And for improving accuracy, I'll do different radius SPAC circles and then merge the results. So we ended up we were able to achieve 3 cones, and 2 of them co-located with SPT. And then we were able to do 5 locations for shear wave velocity. And you see that I did some shear wave velocity measurements down here in the failed material because there was a couple big blocks of material that had rafted along, and we thought that we might be able to image that intact material from those rafted blocks. So these were probably rafted blocks of the dam itself that went for a ride. So 5 SPT, 3 CPT, and 5 passive shear wave velocity profiles. In addition to the lidar, and then from the gear investigations, Rob Kane had done SASW. And here I say 3+1 because we do intend at some point, there's one location that I wanted to go back and push a CPT on one of those, the back tailings dams, and co-locate it with an SPT. And we still intend to do that. We're waiting for a project that's down in that area, and then we'll do a side trip and punch the cone in there. So the intended use, as I mentioned, you know, another point in our post-liquefaction residual strength database. This would be a good case history also for calibrating numerical models. And then we wanted to, you know, try to set a standard for what flow failure case history investigations should look like. And, you know, the stars really aligned on this. I had concepts about doing this, but then the lawsuit resulting in the SPT just gave more impetus to it. And then I started bugging NGL and say, hey, I got this great thing going on in Chile. You know, we just need a little bit of money to pull off the investigations. The results Here's a histogram of the SPT results. And you can see here that in the suspect material, we're looking at our clean sand overburden corrected and energy corrected blow counts on the order of 4 to 5, the majority of it. CPT results. Here, histogram, and we're looking at in megapascals, 1.5 to 2 for our overburden corrected tip resistance. And shear wave velocity on the order of 170 to 180 meters per second, all in that same material. Okay, so the next step was to back analyze this to come up with a residual strength estimate for this failure. And we looked at 2 or 3 different failure modes. We looked at failure of just the foundation material, liquefaction of this whole body of tailings material, liquefaction up here that propagated down, and they all gave very similar results when we're analyzing them. And here is kind of our hypothetical progression of intact to completely failed state. So we know this state right here, we know the intact state, and we know this state right here, we know the failed state, and then we make assumptions as we move and step through time there. So again, here's the original geometry and the failed geometry. And to back out the residual strength or the liquefied strength, we use the incremental momentum method from Weber et al. I had participated doing the statistical analysis on that study, and so I was familiar with the incremental momentum method. And then we had Weber join as an advisor on my graduate students panel. And so he essentially trained the grad student Tristan Gebhardt on this method, and we utilized it to estimate our liquefied strength. And so here I've animated it. We're looking at our intact state, and here's the centroid of mass, and we're tracking that centroid of mass through our time steps until our final geometry. I'll show that again because it's kind of fun. Intact. Final geometry. And that process, very tedious and painstaking process. What we're trying to do is we're trying to balance the geometry and also have it converge at zero velocity after our time steps. And sometimes we need to increase the number of time steps and decrease the number of time steps. And finally, we do this iteration and we get that balance, and then what pops out is an estimate of the liquefied strength. So this is a picture of Tristan's spreadsheet that he used to do the iteration to back out the liquefied strength. And what we end up with after all of that, right, so, not quite a decade worth of work, but we end up with, ta-da, a data point that plots on our corrected blow count versus liquefied strength plot. So here I'm showing it against the Weber et al. 2015 plot, and it plots out fairly nicely. Was not a shocker. We had roughly 2 atmospheres of pressure at the foundation level, and we had those blow counts in the 4 to 5 range, and we ended up with a liquefied strength in American units of about 180 psf. And so you guys all know this. I mean, this is a presentation that I give, that I've given to engineers and the mining engineers and the mining executives. And so here I'm just stepping through our screening analysis when we would do a forward analysis on a tailings dam. So we would want to do investigations, and I always tell them, if you could do both, right? CPT plus SPT, have them co-located. And also measure shear wave velocity at the same time, definitely measure the pore pressures. And get some gradation curves, and measure the plasticity on the material. We want to have a really good handle on the water table. We need to do a susceptibility analysis, then triggering on the weakest layers, particularly in the foundation material. And then we do a post-liquefaction pseudostatic stability analysis using some residual or liquefied strength that we have from our various studies. And if we find the factor safety is less than 1, then we want to assess the consequences and or ramp up the study and estimate some deformations. So here I'm showing typical susceptibility methods, and the fines are going to control. And also, I know that this is not as common, but you can do susceptibility with CPT. Right, I sub C is a very popular factor. Also, from our older study, you can just look at the friction ratio, and if you have a friction ratio is less than about 5%, then it's also in the susceptible range. Then is it going to trigger? And, you know, all the arguments about what methods should be used. From a consulting perspective, unless you're doing a performance-based analysis, you can just take a big magic marker and draw through the lines and say yes or no. And for a lot of consulting, particularly if we're doing some type of screening analysis of tailings dams, this would be sufficient. This was a subsequent study that a colleague and I did, and what's shown here, this histogram here, is the Olson and Stark flow failure case histories, and you can see that most of the case histories that make up that database, and that database, right, the same as the Weber et al. Or Steve Kramer's database, it's really about 30 to 32 data points, right? 30 or 32 case histories. But here we can do some statistics on it, and we say, well, most of them fall out in this range. And so if we've got triggering, and triggering is happening in this low penetration resistance range, then and we have the right geometry for it, then flow failure would be a particular hazard that we would want to investigate. Also shown here is lateral spreading. Usually we see lateral spreading from about 8 megapascals on down if we have the right geometry for it. So we get some data, we run the whole thing, and we get our liquefied strength, and then we do some type of pseudostatic limit equilibrium analysis, and we say, yeah, things are bad. Then what? We could go straight to mitigation, which is often very costly in these situations. We could do some type of probabilistic analysis where we estimate the probability of failure, and we multiply it by the consequences, and then rank that against other risky scenarios, put it into a logic tree, and give that to the decision makers. We can also step it up if the client wants, and we can do finite element, finite difference analysis. There's been some success with discrete element. I'm a big fan of where material point method is going, and so I just threw in this. This is not mine. This is just this really nice animation showing a this is rainfall-induced flow and landsliding. And I've fiddled with material point method a little bit. I tell you what, it's a pain in the butt to build even the simplest models, but I think the being able to capture realistic deformations might be worth it. And so I have hopes that this is going to be used more and more in research and consulting. And so, let's see, it was a sabbatical that I had a couple years ago, and I dedicated a whole week to material point method. And I had been communicating with Kenichi Soga up at Berkeley, and he said, "Oh, this is great," and he sent me, this is how you do it. And so you got this program to set up the file, and you have this program to compile it, and then you have this program, and you run it with the code, and the code's kind of grumpy, and you got to tweak it. I spent a whole week, and I was just sitting at my table like one solid week, and I think the kids were out of town, so I had like this dedicated effort on this, and I was able by the end of the week to achieve where I had a box of sand, and you pull the sluice out, and the sand flowed through the box, and that was dry sand. And I was like, that was awesome, but it took me an entire week to do it. So I was wondering if there was a simpler way to try to estimate deformations for a flow failure type situation. And so in having dug through the literature before, I pulled up this dam break solution from Hunger, and you guys have probably seen this before. It's a very simple physics-based derivation. And I said, well, how can I prove this up? And I haven't published this yet. This is just sitting in that pile of things that need to be published. And what I did is I took the database from Weber et al., so roughly 30 cases, and of those, only a subset of them actually have runout measurements. And there was two outliers. One was the Fort Peck Dam, which had really high stress conditions. And so I limited the stress conditions to 1.5 atmospheres. And then it was the Uitsu railroad embankment that was also a funny outlier, and I made some viscosity adjustments on that one. And with that, I get a fairly good one-to-one relationship, and not shown here is the Las Palmas dam failure, because here I'm doing 50-meter runout, and that data point was way out here at 350 meters, but it lines up right on this. So that was just a little exploratory work that I did, and I think I'm going to kick this out in a paper in Chile, because I think they would be very interested in this. But like I said, I haven't published that yet. So with that, I want to thank all the players that were involved here. My grad student, Tristan Gebhardt, my colleague, Christian Ledesma, down at Catholica, Dave Frost, who was a cheerleader for this whole thing, Joe Weber, who was on Tristan's advisory panel, and then John Stewart, who helped shepherd the peer report to the end and put a lot of time into that. And also I want to thank, the funding from NRC and through SWRI, and, the gear investigations who kicked this all off through NSF, and also Caltrans funding through peer. And the only place that we've published this in its entirety is at the peer report that we finally kicked out in 2019. And yep, that's it. So hopefully you found it an enjoyable story. I know that it was a good, like these arcs of research. It's very fun to see these long arcs of research. We're doing speaking of arcs of research, we're doing a follow-up study right now on the Mataquito Bridge liquefaction and lateral spreading that happened in the 2010 earthquake. So that should be coming out in the next year or two as well. So even though the earthquake was over a decade ago, it's still going to be producing a useful research and fun projects to work on. So with that, I would like to open it up to questions.
Thank you, Rob. That presentation was really great. Thank you for sharing. I did see one question came up in the Q&A. So if you would like to, or yeah, I did make John able to speak. So if you'd like to clarify or ask his question in person, he's welcome to.
Sure. Yeah. Now, just how important is it to understand how dry season, wet season, when you run through make a recommendation for maybe a CPT, SPT, shear wave on your dam, how important would it be to select the right time of year to make sure that you're capturing true sort of standard conditions?
So the water table conditions are not going to have very much impact on the shear wave velocity. With the CPT, we'll pick it up with the different pore pressure measurements, but it's not going to have a huge impact on the tip and sleeve. But for the analysis, it's critical to have to estimate the water table at the time of failure. And so the SPT was done in the dry season. The CPT was done, at the tail end of the wet season. And we had a lot of, and when I say we, it would be Christian and Tristan and I had a lot of discussions about, what was the water table at the time of failure. And so we varied that a lot when we were doing the back analysis to see how much that impacted it. And for the failure where we were looking at liquefaction and the foundation material, it didn't have a huge impact, but when we were looking at liquefaction of the material overall, it had an impact, and the impact that it had was on the runout deformations when we were doing the back analysis. So we fiddled with that water table back and forth until we felt like we had a pretty good handle on the uncertainty that it was imposing on the analysis. In the end, the different failure modes that we analyzed only gave different residual or liquefied strengths on the range of like 168 to about 180. And so it didn't have a dramatic impact on the resulting residual strength or liquefied strength. Hopefully that got to your question, John. Okay. John Bray, what was the horizontal separation distance of CPT and the boring that were co-located? We tried to, for the two that were co-located, we tried to put them within 2 or 3 meters horizontally of each other. One of the difficulties of that is that the SPT was done in, I think it was 2013, and then we got back to do the CPT in 2017, and we had GPS measurements, but it was a handheld GPS, and then we had photos, and so there would be some uncertainty in that, but we were shooting for in the 2 to 3 meter range of co-location. Results of the SIV analysis and Atterberg limits. Let's see here.
I'll also point out to all the attendees, please feel free to put questions in the Q&A box. It should be in the bottom right. Or if you would like to raise your hand, open up the participants window, and you should see a little hand symbol if you'd like to ask your question verbally. It looks like you have one more in the chat, Rob.
I think I got a couple. Let's see. John Bray had a follow-up. Results of the SIV analysis and Atterberg limits. The ponded tailings was in the silt range and non-plastic, and then the dam material was on the fine sand range, also non-plastic. Let's see, Armin. Let's see, I noticed the ground failure perpendicular tailings dam and aligned with the runout direction. Can you point to ocean directionality or an underlying topographic gradient to explain that? Yeah, this failure was really interesting because it flowed out into 2 lobes. There was what we called the south lobe and the west lobe, and south lobe and the east lobe. And the east lobe ran out about 350 meters, and the south lobe ran out about 350 meters, and the east lobe ran out just under 200 meters. And so that added some complexity in terms of back analyzing it. And for our liquefied strength estimates, we went with the longer run out for that to get that lower bound strength. The topography was really interesting. They had taken a very shallow channel. It was more like a swale, and that's where they impounded the material. And the landscape had been changed dramatically with heavy equipment. The mine itself was about 200 to 500 meters up the hill, and it was a hard rock mine that they were then pulling the material out and then processing it. and then ponding it and sluicing it. And like what resulted in two lobes, I couldn't figure it out. There wasn't like a clear topographic warp that resulted in that. It might have been an artifact of how it liquefied and failed. Unfortunately, the eyewitnesses of it, they were the ones that were killed, so we don't have an eyewitness of the actual failure, and, you know, unfortunate for them, and then we don't have that information. So let's see if I've even got close to your question. And so perpendicular to tailings dam and aligned with the location. Yeah, it was a very shallow downslope angle, and when it blew, you know, I've often thought that maybe it liquefied in a couple of places, which resulted in the two lobes and the two directionalities. Let's see. Russell says, how did you back calculate the liquefied strength compared to the Weber relationship? That was using that incremental momentum method, same method that Weber used for his analysis. I don't know if I'm answering your question, though, Russell. Let's see.
I just noticed Russell's hand is up, so I'll let him unmute so that he can, if you'd like to ask in person, go for it.
Hey, Rob, very nice presentation. Now, I did see the comparison, and I did see how you did it, but what was the vertical effective stress? So it looked like it plotted on the Weber line that corresponded to a vertical effective stress of 2 atmospheres, and that seems somewhat high for the actual conditions.
I think so. If we look at the base of the midpoint or those mid dams, as I recall, I would have to look back on the report, but I think we're on the order of 1.5 to 1.8 atmospheres there.
All right, so not too bad then.
Yeah, not too bad. It was not, when we ended up plotting it up, it was kind of like, oh yeah, nice point, confirms the curves. It didn't blow anything out of the water.
Thank you. And
then Armin, let's see. Yeah, there was cracking in the unfailed mass higher up. So there was evidence of liquefaction in a limited sense all over the place. Like in the upper tailings dam, there was some sand boils, and that's one place I want to go back and investigate because it looks like there was a little bit of liquefaction, but it wasn't enough to trigger the flow failure. Because actually on the upside, on the higher tailings dam, the ground drops off dramatically into a different watershed, and there was some crest settlement and there's some cracking. So there it was like incipient. It was like just about to go, but it didn't. Whereas in the mid dam, the whole thing went, and you know, at what point? So that would be a really nice analysis too, is to back that up and then compare how the subsurface conditions differ at all of those two. And then right up the gut of the ponded intact material was a large crack, and there was some sand boils in there. And when we look at the meager amount of information that we have prior to the tailings dams, which is very meager, and then we look at the subsurface conditions based on where we hit intact material below all of the ponded material, we can see some funny topography going on, which appears to give us that center crack right up the gut of the ponded material. So that it looks like there's a topographic high that's under there that's separating a couple little drainage swales that were filled in. And I think that's what resulted in that centerline crack. Let's see. Other questions?
Do you have any more written questions, Rob?
I think I got through them all. I mean, I tried. They were great questions, and I tried to get through them.
One question I have is whether you think void redistribution played a significant role, given the nature of the sediment.
Oh boy. In this case, because there wasn't really, I'm hedging a little bit. So the ponded material, I don't think so. There was a lot of interlayering, but all of the stuff was this non-plastic silt that when I look at the aerial photo of it, you just see these big flow lines. And so I think that material, you had an initiation and everything turned to soup and it just flowed down slope until it reached, equilibrium. I think that maybe of the rafted chunks of the tailings dam that we found downstream, that there could have been some capping that might have trapped the excess pore pressures and floated those a little further than they would have gone on their own. But in this particular case history, I would say that void ratio distribution, if it happened, had a minimal effect on both on the measure back analyzing the liquefied strength, but more so on the deformations. I think the deformations were just it turned to soup and it flowed until it reached equilibrium.
Yeah. Okay. That's always an interesting variable, of course, when you're trying to build models for this phenomenon.
Yeah. If it had been capped, like if they had capped it with some type of impermeable material, that would definitely, or if we were finding plastic layers in there that were acting as cap layers, but we didn't find that. It was just, laminations of different silt gradations, depending on how they ponded it, where they put the pipe and the pipe sluiced out the material and you have it fining as it moves out and as the coarse stuff drops out first and then it fining as it moves out. And you could see that. You could see that in the interlayered material. Very interesting to study that. But I didn't see any situation in the ponded tailings dam material that would lend to some type of impermeable capping that would give you a water blister or, some type of additional kick out of a void ratio redistribution.
Okay.
So super fun project, really happy that it all came together. This is one of those where you keep pushing, and then all the stars aligned. Know that I had here at my university and with Peer as well, I had to be very careful about conflict of interest because here I'm getting, grant money to do investigations, but then hiring a company that I'm a founder of. And so I know with my grants office here, I had to set up an entire conflict of interest panel and submit everything and have them review it to get the rubber stamp for them to say, okay, we realize you're not skimming on this. And, we just paid the expenses on this in terms of gas and MOB and paying our employees and stuff like that. But, sometimes you can get caught in these funny situations where you're like, it may not pass the SIF test if it gets out in the paper. So we covered our bases with the conflict of interest panel on that.
Yeah. As I recall, your budget was rather modest, so no one was
very small. Yeah. If it had been a big budget, I could see somebody, but no, we were just scraping by on this one. We were literally eating beans, and Dave Frost, he just paid his own way. He said, "When are you going to be there?" And I gave him the dates, and then he just showed up, and then wanted to kick around in Chile and hang out and drink whiskey and go out in the rain. He never, I don't know if you guys hang out with him in the field, but he never wears a rain jacket. I'm out in full Gore-Tex, and he's just standing out there in his wool plaid shirt and just loving the rain.
Maybe it's a Georgia thing.
I think so, or an Irish.
So Rob, Kristen told me that she's having some technical trouble getting her microphone to kick back in. I do have one more question for you.
Okay.
Did you ever get a good record of the ground motion at the site?
No, we had a strong motion station that was, Talca was about 20 to 30, by the crow flies, I think it was only about 15 kilometers from the site. So we had a strong motion station And it was a good 3-component strong motion station that was about 15, 20 kilometers from our site. And that's where I estimated the half a G ground shaking. Okay, so
I think we can draw this to a close. So, Rob, thank you very much for being our first speaker at the seminar series. Great job, and thank you for taking all the questions.
Yeah, great questions.
I'm
going to stop sharing now.
So we'll be organizing additional seminars. I think they're about one a month. John, is that right?
Yeah, we don't have the next one exactly lined up, but we will send out information very soon.
One of the things we may try to do in the subsequent seminars is we have a large number of new cases that have been added. By new, I mean relative to sort of the legacy case history database. Large number of new cases, and many of these would be great subjects for these webinars so that the modelers who are attending this meeting can start to get familiar with those cases. So I think we'll try to arrange a series of those going forward. But with that, again, thank you, Rob, and I wish everybody a great weekend.
Yeah.
Okay. Thanks.
Okay. Bye, everybody.